Hello everyone. In the last class, we discussed how earthquakes occur and how they manifest themselves at the Earth's surface in form of fault lines. Today, we will take our discussions forward with some more terminologies related to faults. So, as we have seen that the fault rupture usually manifests itself at the Earth's surface in form of faults. This fault line or the intersection of the fault with the horizontal ground surface has some orientation. That orientation with respect to the north direction is called a strike. So, strike is measured as an angle with respect to north. Further, any line on the fault surface which is perpendicular to this line of intersection also makes an angle with the horizontal plane. So, the angle made by this fault surface with the horizontal plane is called dip. Now, the movement at the fault can occur along different directions. If the movement or the relative sliding occurs in the direction of strike of the fault, we call it to be a strike slip fault. On the other hand, if the relative sliding occurs in the direction of the dip of the fault, we call it dip slip fault. In many of the cases, the relative sliding occurs in a direction other than a strike and dip. In such cases, we call it as a strike dip slip fault. Let us further look into different types of faults. First, we will look into different types of dip slip faults. So, in these cases, the relative sliding occurs in the direction of the dip. So, if the two plates or if the two rock masses on either side of the fault move towards each other. So, among the dip slip fault, we have normal fault where upper rock mass has a relative downward movement. So, as a result of the upper rock mass moving little downward, this causes a tension in the rock mass, which leads to formation of ridges and valleys such as mid-Atlantic ridge, and this movement usually occurs at divergent plate boundaries. On the other hand, if the upper rock mass has a relative upward movement, so as you can intuitively tell that this will cause compression in the rock masses, and as a result young fold mountains such as Himalayas get formed. This usually occurs at convergent plate boundaries. There is another form of reverse fault where your dip angle is very small. Such faults are called as thrust faults. Among the strike slip fault, that is in the faults where the relative sliding occurs along the direction of the strike. So, these faults are usually called as transform or lateral fault. And in this case, we can have two types of fault, left lateral fault or right lateral fault. How to identify these faults? So, if we stand on one of the rock masses and observe the other one sliding, so if the rock mass in front of us slides to our right, we call it right lateral fault. If the rock mass in front of us slides to our left, we call it left lateral fault. Now, once the earthquake takes place, it generates seismic waves. We have seen in the last class. Among those seismic waves, the first ones are the body waves, which gets generated and which travel through the space inside the earth. Among these are the body waves which travel through the mass of the earth, and among them there are different types of body waves such as primary waves and secondary waves. Primary waves, or which are commonly called as P waves, in primary waves or as commonly called as P waves, particles move in the direction same as that of the wave propagation. So, there is a cycle of alternating compressive and tensile deformations. These P waves are the first to arrive at any site, which implies that the velocity among all the body waves is highest for the P waves. The typical velocity range for P waves is 5 to 8 kilometers per second. On the other hand, secondary waves or S waves travel at roughly half of the speed of P waves, and in S waves particles move in a direction perpendicular to that of wave propagation, which means it is a transverse wave, and in this case shear deformation of the material takes place, and therefore S waves cannot travel through fluids. So, as you can say that some of our part of mantle of earth is molten, so the S waves cannot travel through there. So, there will be some regions where you will be getting only P waves and you will not get S waves. So, since S waves travel at a velocity which is much lower than P waves, they usually reach a site after P waves, and the difference in the time can give an idea of focal distance or epicentral distance. We will look into this as we go through the slides. Further on, as P waves and S waves travel towards the earth's surface, when they reach the earth's surface, they give rise to a different form of waves. These waves are called surface waves. Among these surface waves, the prominent ones are Rayleigh waves and Love waves. While in Rayleigh waves, the particle motion is in retrograde ellipse, in Love waves, the particle motion is very similar to S waves. Now, we have to understand, since most of the damage happens in shear, therefore, S waves among body waves and Love waves among surface waves are the most destructive in nature. Now, once we have understood seismic waves, let us try to understand how do we utilize the identification of waves to understand the location of epicenter of an earthquake. So, first of all, we will try to understand how can we determine epicentral distance based on the arrival of P and S waves. So, let us see this through an example. The example problem says an earthquake generates both longitudinal and transverse waves. As we have seen it earlier, the particle motion in P waves is in alternate compression and tension. So, it is very much similar to sound waves, and therefore, we can also call these waves as longitudinal, while the particle motion in S waves is perpendicular to the direction of travel of S waves. Therefore, these waves are also called transverse waves. So, the speed of P waves is given as 8 km per second and that of S wave is given as 4.5 km per second. These are values which are provided in the example problem. However, these values depend on the properties of soil or rock on the travel path. So, which means since our earth is comprising of different types of soil and rocks, these velocities will be varying over the travel path. However, for the problem we are given constant values for P wave and S wave velocities. So, the seismograph at any site records these P and S waves from the earthquake. Now, it is also given that the first P waves arrives 40 seconds before the first S wave, and we need to find the epicentral distance of the earthquake. At this point, we will use the basic kinematic equation, which is d equals Vt, that is the distance is given by the product of velocity and time. So, it will be given by the product of velocity of P wave multiplied by time taken by P wave from source to site, as well as the product of shear wave velocity or the S wave velocity with the travel time of S wave. So, here we are given Vp equals 8 km per second and Vs as 4.5 km per second. Tp and Ts are individually not known because we do not know when the earthquake actually originated and how much time did these waves take to travel to the site or travel to the seismograph station. But what we know, the difference between these two time is given as 40 seconds. Now at this point we should also understand that since P waves travel much faster than S waves, therefore the time taken by S wave will be larger. So we know that Ts minus Tp equals 40 seconds. We will substitute the value of Ts as d divided by Vs and Tp as d divided by Vp, and upon solving further, what we get the value of d to be 411.4 kilometers. So the epicenter is located at a distance of 411 kilometers from the recording station. Now this is further taken forward to locate the epicenter of the earthquake. So the first thing to do while locating the epicenter of an earthquake is that we need to have P waves and S waves recorded at 3 record stations. So each of these 3 record stations should be recording both P and S waves. From there we will calculate the epicentral distance at these record stations using the time interval between arrival of P and S waves, very similar to what we have discussed in the last slide through an example problem. So now we know that from this location the epicenter is located at x distance away, but we don't know in which direction. So we can draw a circle around the point, around the record station, and the epicenter of the earthquake will lie somewhere on the circle. So that's why what we will do is that we will draw circles centered at record stations, at all the 3 record stations, with radius equal to the respective epicentral distance, and from there we will find the point of concurrence of the 3 circles to locate the epicenter. So it is important to record P and S waves at 3 record stations. If we get the record only from 2 stations, the circles may intersect at 2 points, so we may not get the epicenter. But if we obtain the P wave and S wave records at 3 stations, we are most likely to get a common point or the point of concurrence of the 3 circles to locate the epicenter. At times it may happen that one of your record stations is located further away, and in that case you may not be, at times it may happen that one of your record stations is located in a shear wave shadow zone where your S waves are not reaching. So you will not be able to use data from that record station because you don't know the time interval between arrival of P and S wave at that record station. So this is how you locate the epicenter of an earthquake. Thank you.